Hello, Dr. Schreifels here again. This video is going to be devoted towards trying to understand how to solve some more additional problems that having to do with gases. And in particular, we're going to solve three problems, one with density, one with figuring out the velocity, and one with effusion. The problem shown here is you're given the density of Cl2, told that it's at some temperature. You don't know the temperature or the pressure, but you have the density. And you're asked to figure out the density of propane at the same temperature. So the relationship we're going to use is the one from our gas toolbox on density. So that's this one. Now, you look at that and you say, okay, I have two unknowns. I know R, but I don't know T and P. So what do I do? Well, you don't need to know them, because in the two experiments, density of Cl2 and the density of propane, they are constant. So if we just take the RT over P and replace it with K, the proportionality constant, we can, some people would take this relationship and figure out what K is for Cl2 and then apply it to propane, and that's okay, but you can do it a little different way. So let's take and write an equation for each gas that would look like this. So we have the density of Cl2 equals formula mass of Cl2 times a constant, and the same thing for propane, same constant RT over P. Now, algebra, so you know the density of Cl2, you know a formula mass of Cl2 and the formula mass of propane. You don't know either K or the density of propane, the C3H8. So we want to eliminate variables so we can solve for the variable that we want. So let's take the two equations and divide one into the other. So if we do that, we get this. Notice that the K, because you're dividing one equation into the other, you have K over K, and the K's cancel out. Alright, so now we're pretty close to where we need to be to actually put numbers in it. We want to redo algebraic manipulation to solve for our unknown. So then we can put numbers in after that and solve for the actual value of the density. So here is the rearranged form of the equation above. Now we know the density of the Cl2 because that's given in the problem. And we also know the molecular weights of Cl2 and propane, so they are here. And that leads us to coming up with a density, predicted density of 1.09 grams per liter. And so that was actually a fairly straightforward problem, wasn't it? So now let's work another one. So this one deals with Rms velocity. So let me copy the problem into this. So we know we're after figuring out the root mean square velocity. So we're given, we want to know that in meters per second for ammonia at 831.9 degrees centigrade. So we go back to our toolbox up here and we look for, this is the one that deals with the velocity. U in this is the root mean square velocity, which is what we're after. So let's put that down here. And that's what we're going to use to solve this problem. So now we, key issue here is that we got to make sure, for this all to work out, we got to make sure we have the gas constant, the temperature, and M, the molecular mass of the compound, in the right units. So what units do we use? Well, T, we almost always should be in Kelvin. Your gas constant should be 8.3145, and I'll prove to you later that why that's the case. So there's our gas constant, and then of course the M is the molecular mass, and that should be in kilograms per mole, not grams per mole, kilograms per mole. All right, so let's take the values that we're given, and we're going to put them into our gas equation for the root mean square velocity. We're just going to directly substitute in there for the numbers that were given. So here's the 3R. R is the 8.3145 joules per mole Kelvin. The temperature, you convert that to Kelvin, so you know how to do that. Add 273 to the 831.9 to get 1105, and then ammonia's molecular weight is 17 grams per mole, or 17 times 10 to the minus 3 kilograms per mole. So that's the root mean square velocity. Now you notice that there's moles are in red, and you can see you have moles over moles, so those are going to cancel, and the Kelvin over Kelvin are going to cancel. So if you take the numbers and figure out what the result is, you'll get 1270, and then take the square root of it, you'll get 1273. Now, some units didn't cancel. The joules and the kilograms didn't cancel, so we have square root of joules over kilograms. Now, the thing the reason why we use that gas constant is because we get joules in there, and if we look up in the book, you'll see that a joule is 1 kilogram meter squared per second squared. So in place of the joules, we'll put in the kilogram meter squared per second squared. And so in the next equation, I've done that. So there it is. Now I've accented the kilograms because they cancel out, and you see you left with meters squared per second squared. Whoops. Let me fix that per second squared there. It should have been, let's try again. There we go. So meters squared per second squared, when you take the square root of those, you end up with meters per second, don't you? So that makes our final answer, after a little modification in what I had, this. So that ammonia molecule, when it's at that temperature, is moving 1273 meters per second. Pretty fast, huh? Okay, well that's the using the root mean square velocity relationship that we have in our gas toolbox. Now the last problem is Graham's law of effusion. So here, I'll paste that into here. So you can see that we have an unknown gas effuses through a small opening slower than nitrogen does, and we're asked to figure out the molecular mass of the unknown compound. Now we don't know temperature, we don't know pressure, we don't know anything like that. How do we solve that problem? Well, we go back to our toolbox, and you see here's a problem having to do with, an equation having to do with effusion. Copy that. I'm not sure I copied it the first time, so here we go. Now let's put that there. Now this one's maybe not so obvious because you see that proportional sign. This symbol right here just stands for it's proportional, and we can replace that with an equal sign if we put in a constant k, like that. And now we're ready to actually figure out the answer to this. But we start by recognizing that what this problem is telling us when it says that it's the unknown gas is moving slower than nitrogen through that hole is it's saying that the rate of the ratios is 1.103. That is, nitrogen's going 1.103 times faster than the effusion of the unknown gas. Right off the bat, because these are inversely proportional to each other, that should tell us that the answer we're going to end up with is going to be greater. The molecular weight of the unknown gas is greater than it is for nitrogen. So like we did before, to get rid of the constant, you can algebraically do this. So now we have, I put in the number for the relative rates. We can rearrange this thing for the unknown and put in our values for that we know. So we just need to put in the molecular weight of nitrogen, which is 28, and I've rearranged this thing to solve for the mass, molecular mass of the unknown, and so you end up with an answer of 34 grams per mole, which of course is exactly what we predicted it would be in relative magnitude. We expected the molecular weight of the unknown to be greater than the molecular weight of nitrogen. Okay, so I think I covered 3 problems that I was wanting to help you with. I hope you find this helpful in understanding what to do when you encounter problems that deal with gases and how to solve them. I think it should be less difficult than many of you think, and I hope that you do well on your studying and learning how to solve these kinds of problems. Have a great day. I'll see you soon. Bye-bye.